Good afternoon. So in today's lesson, the goal is to go over 3 more examples of homogeneous boundary value problems, just to review what we learned so far. This lesson is the last one in the first half, so the second half of the course is already recorded using a different camera, so not a writing tablet like in this case, but just a camera over the desk. At some point, I'm going to ask you, those of you who are my students, whether you, well, actually not just my students, but if you have a preference of actually seeing the hand moving over the paper, if you find that makes it valuable in some sense. I mean, it obviously makes it easier to point out to various parts of the paper, but I'm curious if the benefit is really that important, because the writing tablet is, preferable to me at least than the camera over the desk. But anyway, back to the topic of today. We're going to go over, like I said, over a couple of more homogeneous boundary value problems. The next lesson after this will be it'll be a situation in which a problem in spherical coordinates can be actually reduced to one in Cartesian coordinates, or similar to the one in Cartesian coordinates, to be more precise. And because in general, if you move to different coordinate systems like spherical or cylindrical coordinates, the problem changes in a radical way. You need different types of series, not the cosine or sine series. And in general, from this point on, once we learn well how the separation of variable method works, from this point on, we just focus on situations that change some of these steps in the separation of variable method. So for example, in a couple of lessons from this point on, you will see an example in which the ordinary differential equation of the other equation, not the Sturm-Liouville problem, but the one in T, for instance, it's different. So it's a different type of ODE. And then 2 major chapters are there because the Sturm-Liouville problem is different. Also, coming from a change in the problem, like for instance, using different coordinates, like spherical or cylindrical coordinates. But for now, let's fix the notions that we learned so far. We're going to take for granted, in the interest of time, we're going to take for granted that these Sturm-Liouville problems, the result of these Sturm-Liouville problems that you see here, the one with Dirichlet conditions, and the one with Newman conditions, x prime of 0, x prime of c equals 0. So once we conclude via separation method that one of these is the Sturm-Liouville problem that comes up in the problem, we just use directly its result. In other words, we're going to assume that the eigenvalues and the eigenfunctions are the ones given here. So have that in front of you, and also the guidelines of separation of variable method, that handout that I distributed earlier. So the first example, it's a heat equation. So let's say ut equals 4u partial x twice, and then the initial condition u of x0 is x. I often use x. I'm going to change it obviously at some point, but I use x often in the interest of time because the corresponding series, Fourier series, is shorter. X between 0 and 1, and we have Dirichlet type conditions at the boundary points. U of 0t equals u of 1t equals 0. So with a little experience at this point, you should already anticipate that you will need the first Sturm-Liouville problem above. So this one leads eventually to that eigenvalue problem. So let's see where that comes from. So we assume, as always, that the u of xt has the product form. And again, from this point on, feel free to write it just x times big T, as long as there is no risk of confusion. So as long as you always remember that big X depends on little x and big T on little t. And then plug in the product form into the full problem on the left. So on the left side, we're going to have x t prime equals 4x double prime times t. We can leave the initial condition aside, because we know already that this will be dealt with after we use the superposition principle. but we do plug in the product form into the boundary conditions. See here, I don't write just xt because notice that here little x is 0. It's evaluated at 0, right? So this is going to be x of 0 times t of little t equals x of 1 big T of little t equals 0. If this is to be true for any t, this implies x of 0 equals x of 1 equals 0. And then when we separate the PDE, we end up with x double prime over x equals t prime over t over 4t equals a separation constant, which is denoted by minus lambda. So if you forget where that comes from, just go over the algebra one more time. Or you can just check the cross multiply and check. So notice that if I take the equation in, well, let's write the equation in t prime, because we're going to deal with that later. So t prime equals minus 4 lambda big T. And the equation in x double prime, in x, big X, is going to be x double prime equals minus lambda x. If I move it to the left side, it's going to be x double prime plus lambda x equals 0. And then together with the boundary conditions on big X. So now you say, okay, I recognize this is the eigenvalue problem above, which I said to take it for granted, in which C is equal to 1, right? So that's on the interval 0, C, in your case is the interval 0, 1. So just immediately write down the eigenvalues and the eigenfunctions, n pi over 1 squared, which is of course n pi squared, and then the eigenfunctions sine of n pi x over 1, which is sine of n pi x. So never forget the logic of all these steps, right? So what the, okay, and then it's from 1, 2, 3, and so on. So what we accomplished so far, we just found infinitely many solutions. Take a look at this, where I show you with the pencil. We have infinitely many solutions for the first half of that product form. So for big X or little x. So for each version, that is to say for each n, we have to solve the equation in T to find the other term of that product form. So for each lambda n equals n pi squared, we're going to solve the equation for big T. So now it's time to plug in lambda n. So we have minus 4 n pi squared big T. Just for aesthetic purposes, you might prefer to write it like that with everything into a power of 2. So big T prime equals minus 2n pi squared big T. That's a first order ODE. And its solution is a constant e to that constant minus 2n pi squared times little t. Remember the convention of notation. That constant of integration, when you solve this, label it n, like an, not just a, because you have to remember you do this for every n. And the solution itself is indexed by n. So Tn is going to be an e to the minus 2n pi squared little t. Again, where n is 1, 2, 3, and so on. All right, so that means we just obtained infinitely many solutions for u. Un of xt is xn of little x, tn of little t, which is to say an, I'm going to put the constant in front, an xn was, what was it, sine of n pi x, and tn of t, an e to the minus 2n pi squared t. So this is how each of these infinitely many solutions looks like for the full PDE. All of them satisfy all conditions because we imposed all conditions except the remaining one, which is the initial condition. So now superposition. So therefore the full solution we're looking for is the summation as n goes from 1 to infinity of these infinitely many solutions. all I have to do now is to determine an such that the initial condition is satisfied. So I'm going to plug in 0 for t, e to the minus, you can do this faster, I just want to emphasize it one more time. So that's e to the minus that constant times 0, that becomes 1. So this becomes 1, so this should be equal to x. So that means I need a Fourier sine series for x on the interval 0, 1 to determine an. If I look in the table, remember to change the interval. So in the table, you're going to replace x with pi x to change the interval from 0 pi to 0, 1. So you're, in other words, in case you forgot this step, because let's put it here in this corner, because your x is between 0 and 1, and the table gives you the interval 0 pi for that series, you have to substitute x with pi x so that you can bring it into the series of the table and then let x by itself. So if you do that correctly, then x is going to be equal to summation, well, 2 summation from 1 to infinity, 2 over pi actually, because you move pi from the left to the right. Summation from 1 to infinity minus 1 to the n plus 1 over n sine of n pi x. We can bring 2 over pi inside the summation. So once again, the solution, I'm sorry, u of x 0 on one hand coming from that solution is the summation from 1 to infinity an sine of n pi x. This should be equal to x, which from the table is equal to the summation from 1 to infinity 2 over n pi minus 1 to the n plus 1 sine of n pi x. So from this equality, we see that an must be equal to 2 over n pi minus 1 to the n plus 1, and that's it. Yeah, 2 over n pi minus 1 to the n plus 1. Okay, so at this point you can stop, although technically to provide the solution, again, for the full problem, you have to basically bring back an that you just found all the way back to u of xt, right? This is your solution. But, you know, in order to not waste too much time, because these problems are already rather long, as soon as you find the coefficients and you state them, I mean, you write down what those coefficients are for the final solution, then you can claim victory. I mean, you can say, okay, that's it, that's the solution, that's what an is. If you have time, you can bring it back into the formula for u of xt. All right, so let's move on the second page with more examples. All right, so our second example is another heat equation, this time with Newman conditions, which, by the way, in the context of the heat equation, that means the endpoints are insulated. So let me write down the full problem though. So the interval is 0, 5. Let's say the initial condition is x squared, u of x0 equals x squared, and then u partial x of 0t equals u partial x of 5t equals 0. And like I said, this means insulated endpoints. So the meaning of this means insulated endpoints of that bar. Because remember, the flow of heat is that conduction term times the temperature gradient. So to say that this is 0 means that the flow is 0. Right? So that means there's no transfer of heat on the endpoints. So if the problem states in words that this is an object with insulated endpoints, that means you have Newman conditions, right? U partial x at 0, t u partial x at 5t equals 0. Okay, so let's get to solve it. Again, the product form, just like before. We're gonna plug it in. So we have xt prime equals 9 x double prime t. You know the drill already, I hope. So x double prime over x is t prime over 9t equals minus lambda. And let's plug in the product form also into the boundary conditions. So notice that u partial x at xt is x prime of little x big T of little t. Then you're gonna plug in 0 for x, right? So x prime of 0 big T of little t is x prime of 5 big T of little t equals 0, which implies x prime of 0, x prime of 5 equals 0. So the equation in t is t prime equals minus 9 lambda t. And let's write it from the left side. The equation in x, the eigenvalue problem, or the Chernobyl problem, is x double prime plus lambda x equals 0, together with x prime of 0 equals x prime of 5 equals 0. Now look at the previous page. The eigenvalues and the eigenfunctions for these problems are the following. You have 0 as an eigenvalue with 1 as an eigenfunction, and then also lambda n with n pi over 5 squared as an eigenvalue, and the corresponding eigenfunction will be cosine n pi x over 5, where again n is 1, 2, 3, and so on. So don't forget, like I said, the pair that corresponds to lambda equals 0, which happens in this case, unlike the previous case. Okay, so now we go back to the equation in t, and notice, because we have two sets of eigenvalues, the 0 and the n pi squared over 5, we have to solve that equation in, you have to solve it twice, right? One for lambda 0 and one for lambda n equals n pi over 5 squared. So when lambda naught is equal to 0, then the equation in t becomes t prime is equals, well, 0, which means t is a constant, and t naught, let's call it t naught of little t, is just a constant, and let's denote that by a naught, because we're going to sample that in a using the superposition principle. Because you see, like we do the same in the other equation. The constant of integration will be denoted by a indexed by n, which in that case then goes from 1, 2, 3. So that's why it makes sense to call this one a naught. Any notation will do, because when you do the superposition principle, again, this will be a constant in that linear combination, which will be determined from the cosine series at the end. So, and then the next one, lambda n equals n pi over 5 squared, leads to the equation t prime equals minus 9 n pi over 5 squared big T. Let me write it again on the left side, just to put everything into a power there, just again for aesthetic purposes. I mean, obviously I chose these constants to be square so that they look nice. You don't have to do that, but I can bring n inside that square and write it as 3n pi over 5 squared big T. Again, that's an exponential, so Tn of little t, its solution will be a constant, an, times e to that, to minus 3n pi over 5 squared little t. And now we do superposition principle. So we're looking for the full solution, right? So we have infinitely many solutions, xn times tn, x naught times t naught. So we have xn times tn with n from 1, 2, 3, and so on. X naught t naught, which is separated from this. So we're going to start with x naught t naught. So u of xt is a linear combination of these. So the first one is going to be a naught times 1 so this will be, make it clear, this will be T naught X naught plus the summation from 1 to infinity. I should have started with xn, doesn't matter anyway, xn, which is and as always let's put the constant in front of everything, xn, which is cosine of n pi x over 5, and then tn e to the minus 3n pi over 5 squared little t. All right, so finally now let's impose the initial condition, which is u of x0 equals x squared. So again, this is your solution, but now the question is, what is a naught, what is a n that satisfy the initial condition? So u of x0 on one hand is a naught plus the summation from 1 to infinity a n. So if I replace t with 0, e to the 0 is 1, so you're left with cosine of n pi x over 5. And this should match x. So the question is, you need x as a Fourier cosine series on the interval 0, 5. So if I look at the table, we have the Fourier cosine series on the interval 0, c. So x squared is 2c squared summation from 1 to infinity minus 1 to the n plus 1 over n pi minus 2, 1 minus negative 1 to the n over n pi third. Oh, sorry, I'm looking at the wrong series. I was looking at the sine series. One more time. So x squared is c squared over 3 plus 4c squared over pi squared, the summation from 1 to infinity minus 1 to the n over n squared cosine of n pi x over c. So we have this on the interval 0, c. So all I have to do in my case is to replace c with 5. And I say, okay, x, not x, I'm sorry, x squared here. So x squared on the interval 0, 5 is going to be, if c equals 5, is going to be 25 over 3 plus 4 times 5 squared, which is 25 again, over pi squared. The summation from 1 to infinity minus 1 to the n over n squared cosine of n pi x over 5. So now you just have to state what a naught and a n is. So look carefully. A naught obviously is the constant term in the Fourier cosine series, and a n, look carefully here, a n is everything that's multiplied by cosine of n pi x over 5. So it's gonna be this, and don't forget the constant on the outside, which you can bring it inside the summation. So a n ought to be 4 times 25, which is 100 over n pi squared, combine pi squared with n squared, minus 1 to the n. So let's actually bring them all the way back into the full solution. So the full solution of the problem, u of xt equals a naught, which is 25 over 3. You don't have to do that, like I said. I mean, once you determine a n and a naught, you're done. But just to put them back into the full solution, so summation from 1 to infinity a n, which is over here, cosine of n pi x over 5 e to the minus 3 n pi over 5 squared little t. And that's the solution to this problem. So in my last example, I'm going to go over a wave equation, but you'll see it's actually different than the ones I went over before. So that's why it's so important to go slow and make sure you do every single step carefully. Once you recognize one of these steps are being done before, you can take it for granted, like we normally do the eigenvalue problems. But besides the eigenvalue problems, you really have to be careful because conditions may change, different conditions may change how you come up with these coefficients. So actually, besides the Sturm-Liouville problem, you can't really take for granted anything. You just have to go through all the steps carefully. So let's stay tuned for the last example. All right, so let's do a wave equation. So yt twice, partial t twice on the left equals 4yx, partial x twice on the right. And the interval for x is 0 pi. But in this case, notice I'm going to actually have non-zero initial conditions for both the displacement, the initial displacement, and the velocity. So previously we had zero initial velocity. So this time let's actually do non-zero initial conditions. It's still a homogeneous, the boundary condition is still homogeneous. So we have y of 0t equals y of pi t equals 0. And let's see how this changes the situation. So because it's worthwhile to comment on this a little bit. So let's do all the steps first, which are the same, you know, taking the product form and plugging in, and let's see what we end up with. So we have y of little xt equals big X of little x, big T of little t. And then if I plug it into the PDE, that gives me big X t double prime equals 4x double prime big T. Separate, so that gives me x double prime over big X equals t double prime over 4t equals minus lambda. So you see the difference is that there's no extra condition on big T, because that condition on big T came from zero initial velocity. So actually, I'll get back to that remark at the end of the problem. Because if you look at the previous problems that we did on the wave equation, because the initial velocity was 0, that gave me a condition on the equation in big T. But here we won't have such a thing because this initial velocity is going to be non-homogeneous. So the only conditions we're going to have are for big X coming from the homogeneous boundary conditions. So I plug in the product form into the homogeneous boundary condition. So that's x of 0 big T of t equals x of pi big T of little t equals 0, which gives me x of 0 equals x of pi equals 0. Because remember, the rule is that you plug in the product form into all homogeneous conditions. So previously, since we had 0 velocity, you would have to plug in that product form into that condition as well. But here we don't have 0 velocity, so you just have the boundary condition. So that's it for the product form. So in other words, the two ODEs are t double prime plus 4 lambda t equals 0 without any extra condition. So we'll get back to this later once we're done with big X. And of course, the Chernobyl problem, which is the familiar one, x double prime plus lambda x equals 0, together with x of 0, x of pi equals 0. So we know the solutions of this. So we know that that gives me lambda n equals n squared. And the eigenfunctions corresponding to these are sine of nx for n from 1, 2, 3, and so on. And now for each lambda n, we solve the equation in T. So plug in lambda n, that's n squared. That's a second order ODE. Keep in mind the characteristic equation is r squared plus 4n squared, which has the complex roots, as you will got used to it already because it appeared before this equation, plus minus 2ni. And that means the solution for Tn of little t depends on two arbitrary constants, which we denote them by an and bn. So we have an cosine of 2nt plus bn sine of 2nt. So previously, since we had zero velocity, we would impose that condition here. It was t prime of 0 or something like that. Here we don't have any extra conditions on big T. Since we don't have any extra conditions, then it's time to do superposition principle. But now, after we do superposition principle, we have to match two non-homogeneous conditions, which kind of makes sense because now we have to basically figure out two sets of constants for the final solution, an and bn. So that makes sense. You have basically now two remaining conditions to impose. So superposition, that means y of xt will be in the form of the summation from 1 to infinity, tn of t, let's start with that. So an, let's put that in a big parenthesis, an cosine of 2nt plus bn sine of 2nt times sine of nx. And we're going to need also the derivative of this with respect to t for the second initial condition. So y partial t of xt, partial t we differentiate inside this parenthesis, that gives me minus 2n an sine of 2nt plus 2n bn cosine of 2nt sine of nx. And now let's plug in the conditions. Y of x0 should be x. So y of x0, notice, is going to be summation from 1 to infinity an cosine of 0, which is 1, plus bn sine of 0, sine of nx, which ends up being summation from 1 to infinity an, this is 1, this is 0, an sine of nx equals x. So an comes from the Fourier sine series for x. So on the other hand, x is equal to, looking at the table, the sine series for x on the interval 0 pi is 2 summation from 1 to infinity minus 1 to the n plus 1 over n sine of nx. So that means an must be 2 minus 1 to the n plus 1 over n. And then, you guessed it, the second set of constants, bn, comes from the second initial condition, the initial velocity. So y partial t of x0, if we plug in 0 for t again into that derivative, pay attention here, we end up with minus 2n an sine of 0 plus 2n bn cosine of 0 sine of nx. And that should be equal to x third. Now x third on the interval 0 pi as a Fourier sine series is gonna be 2 summation from 1 to infinity minus 1 to the n plus 1 n pi squared minus 6 over n third sine of nx. Make sure I copied that correctly. All right, so pay close attention here because that's a little common mistake at the end of the problem here. So the left side of this summation, because again sine of 0 is 0, cosine of 0 is 1. So what we have basically when we match these series, we have on the left 2n bn sine of nx, which matches on the right hand side that series. Let's bring 2 inside. So you have 2 minus 1 to the n plus 1 n pi squared minus 6 over n third sine of nx. So 2n times bn must be equal to this coefficient over here. So bn alone is going to be that coefficient over 2n. So I have to divide by 2n the coefficient on the right hand side. You can cancel the 2, so you can multiply n with n third, so that gives you minus 1 to the n plus 1 over n fourth n pi squared minus 6 in the parentheses like this. So that's bn equal to. So remember that 2n comes from the derivative, right? It's just the chain rule when you took partial t. So I hope it's clear. As you can see, we can handle actually, two non-homogeneous conditions in this case. Essentially, for the method to have a chance to work, you need, let's put it this way. For the method to work, it needs to produce a homogeneous Chernobyl problem, which is a homogeneous boundary value problem for an ordinary differential equation. So in other words, you need to have enough homogeneous conditions, boundary conditions, so that you have basically infinitely many solutions, which allows you to assemble the full solution in the form of a series with coefficients yet to be determined, and hopefully those coefficients will come from imposing the remaining non-homogeneous conditions. So I think that's it for today, and I'll see you next time.